Welcome. This video details some of the scientific accomplishments achieved by the Heliophisics Science Division throughout 2010. Our mission is to explore the Sun, understand its variability, its influence over the Earth and other bodies in the solar system, and the interactions of the heliosphere with the interstellar medium. 2010 started with the successful launch of the first Living with a Star mission, the Solar Dynamics Observatory, led by Dean Pesnell.
T-minus 30 seconds and counting.
Go ahead, no sensor.
T-minus 5, 4, go for main engine start, 1, and ignition, and liftoff of the Atlas V with the Solar Dynamics Observatory, learning why our star is changing our lives.
As SDO soared into its geosynchronous orbit, it opened a new era in solar exploration. It carried instruments that can look deep into the solar interior, observe how the corona responds to changes in the Sun's surface magnetic field, and monitor the EUV emissions that are most influential on the Earth's atmosphere. These instruments have high spatial and temporal resolution, extensive spatial and spectral coverage, and almost continuous viewing of solar activity with high data rates. These capabilities will give us unprecedented views of phenomena that we have only had a chance to glimpse in the past. Our high hopes for the mission were more than justified when some of its first images captured the spectacular prominence eruption, showing vast amounts of plasma being ejected into interplanetary space while the twisted magnetic fields unravel. Soon thereafter we saw this dynamic flare event where we can see in detail the evolution of the reconnecting magnetic fields with superb time resolution. As SDO takes its place as part of the Heliophisics Great Observatory, it has already started to work in concert with other elements of the solar network, RESI, SOHO, Stereo and Anode, each providing data addressing a unique aspect of solar activity. For example, in this sequence, SDO observes an eruptive event on the East Limb seen simultaneously by the Stereo B spacecraft from above. These multi-aspect observations enable us to derive the three-dimensional structure of the optically thin coronal plasma. Using data like these, Bill Thompson has managed to track individual features in a coronal eruption and reproduce their three-dimensional evolution. Similarly, Terry Kuchera and her collaborators have used stereo coronal images to model the spatial structure of this coronal cavity. In this sequence, Spiro Antiochos has used Hinode X-ray images to follow the evolution of coronal jets in a coronal hole. Combining these data with simultaneous observations from stereo, it was found that many of the jets demonstrate a twisting motion. Spiro has been able to reproduce this effect in a fully three-dimensional MHD model. RESI observes the highest energy emissions from the Sun. It has recently observed two plasmoids apparently merge. This collision was coincident with the acceleration phase of a CME with a likely link to a magnetic reconnection and particle acceleration event identified by its radio emissions. We cannot leave the Sun without acknowledging the end of the TRACE mission, which was a SMEX that cost only $40 million and lasted for 10 times its design life. Perhaps its most notable accomplishment was that it pioneered the NASA open data policy, which resulted in over 1,000 publications using the TRACE data. Moving out into the heliosphere, a comprehensive study of SOHO, wind and ACE data, led by Nat Gopalswamy, has shown that CMEs are the driving force behind interplanetary shocks, even those that until now were thought to be driverless. Conversely, ripples in the solar wind were often thought to be driven by CMEs, but in a recent study the ripples were found to be the result of interactions of slow plasma streams being swept up and compressed by fast solar wind. Again, the capability of the stereo spacecraft to observe the same phenomenon from different aspect angles made the resolution of this issue possible. Dustin Ostrasil developed this animation that shows the predicted solar wind velocity at each of the planets and calculates the temporal profiles that would be observed at various NASA spacecraft, such as Stereo, Messenger and ACE. The solar wind has been observed to be hotter than predicted by the models, and a fortunate configuration of the four-cluster spacecraft has discovered why. For nearly an hour they were close enough together for them to observe small-scale turbulence. It was found that protons in the solar wind are heated by the cascade of turbulence to ever smaller spatial scales. Nikki Weil has shown that the periodic density structures in the solar wind must originate at the Sun and are not caused by local turbulence as once thought. Such solar wind variability is seen to affect Mercury's magnetosphere. Messenger's third flyby of Mercury has confirmed that its intrinsic magnetic field is unchanged, but its magnetosphere is highly variable in response to variations in the interplanetary magnetic field. In geospace, AIM has been monitoring the seasonal variation of noctilucent clouds, seen when tiny ice crystals form high in the Earth's atmosphere and are illuminated by a low sun angle. These are the highest altitude clouds formed. The outer boundary of the solar system is not without change either. A second IBEX map of the heliosphere has shown variability, especially at the two poles. Overall, ENA emissions in the second map are lower than those in the first map. HSD takes a leading role in education and public outreach, with a variety of educational programs for people of all ages and events designed to keep the general public informed of our activities and discoveries. For example, there is Sun Earth Day.
Our sun has always been more than a ball of heat and light. Our sun, through curious minds and innovative technology, has allowed us to explore how the northern lights dance and how our solar system may have formed. The sun is ours to discover.
HSD not only manages most of the Heliophisics programs, but plays an active role in the collection, archiving, analysis and publications of data collected by NASA. In 2010, our scientists have authored and co-authored over 700 papers and presentations. In this video, we've only been able to touch on a few aspects of that work. More extensive details of our efforts are available in the HSD annual report and at the HSD website.